So it's great pleasure to have the Yikun Jiang from Cornell, used to be Fudan. He's going to talk about the islands and cosmology, or how to look for islands.
Yes, thank you, Satoshi. And it's a great pleasure to be back virtually at Fudan. So I will basically talk about this paper recently came out with my supervisor at Cornell, Tom Hartman, and our postdoc, Edgar Shaghoulian. And Satoshi just told you the title, and I hope after my talk, it'll be clear what these two parts are about. Okay, so the plan of the talk will be fourfold. So first of all, I will try to give a complete but brief review of the information paradox and the quantum extremal island prescription. One more thing to say is this is actually my first talk to the public and the first one to be recorded. So I'm sure something probably will not be so clear. So if you have anything that you find suspicious, just don't hesitate to unmute yourself and ask me questions. Okay. And after this, I will tell you that actually we want to look for more islands other than the ones existing in literature. So, oh, sorry, is there a question? Oh, yeah, okay. So, and we will try to derive some constraints actually using quantum information theory on the existence of islands. And we will see actually these constraints are very restricted. And just using these, is there a question?
I don't think so, sorry. I think I will unmute the opponentry, sorry. I will
okay, yeah. Okay, yeah, no worries. So, and then we will see using these constraints as guidance, I will try to show you some examples where we find islands in cosmologies. Especially, I will focus mainly on this 3+1 dimension FRW because currently there are very few examples actually for these islands in higher dimensions. And finally, if we have time, I will comment a little bit in 1+1 dimension, this de Sitter space JP model. Okay. So first of all, let me try to review. There is a exciting development last year for the understanding the information paradox and these island stuff. So what actually is the information paradox? So the information paradox, to summarize in one sentence, is Hawking discovered in his groundbreaking work that black holes evaporate. And the evaporation spectrum, radiation spectrum, is thermal. So suppose we have a black hole formed from collapse. Before it collapses, there is a star, so we have a pure state. And finally, you can wait long enough time, you collect all the radiation, the black hole evaporates completely. And finally, we collect all the radiation, they're in a thermal state. So it seems that the pure state can evolve into a mixed state. This is the usually stated paradox. And this clearly violates the rule of quantum mechanics. But you might argue, because we need to wait until the black hole completely evaporates, it's definitely outside the validity of semi-classical gravity. So is this really a paradox? Is it because we don't know some details for quantum gravity? Actually, no. There is a sharper diagnostic, which is called the page curve, which is telling you this paradox arrives much earlier than the final destiny of this black hole. So the paradox runs as follows. There are two kinds of notions of entropy. One is the fine-grained entropy, which is our favorite von Neumann entropy. So you have a density matrix, you just calculate minus trace rho log rho, which is, yeah. And the other one is the so-called coarse-grained entropy. And this one involves a step. So our familiar thermodynamical entropy is this kind of coarse-grained entropy. It essentially tells you the maximal room, the amount of information a system can have. So suppose now I collect the radiation here. I'm using for first part, I'm mostly using this diagram in flat spacetime. I collect all the radiation at non-infinity and gradually evolving with time. So when I collect more and more radiation, the radiation just grows. And this is what Hawking tell you because the radiation is thermal and I'm just having more and more Hawking quanta, so-called. So it grows forever. However, the thermodynamical entropy is famously given by the area over 4G Newton. And because the black hole evaporates, the area shrinks, it actually goes down. So you will immediately, yeah.
Well, I have a question
yeah, sure,
already. since we have local time, so I guess I can ask some questions at the very beginning. So my question is about the right panel of your figure. So as we know that when we have Hawking radiation, the black hole horizon shrinks because the mass gets lost by Hawking radiation. And we know this horizon is actually that the event horizon actually becomes the dynamical horizon. And at some point, this horizon is not null surface anymore. It's actually time-like surface. And did people recently doing this work and take this into account? Well, it seems that all the figure people use are always this kind of event horizon, not really which is not completely true. Yeah. So yeah, this is that. Did people take that into account?
And does that solve the information paradox? Like, is there still a paradox?
Well, dynamical horizon, of course. No, I'm not saying dynamical horizon solves the information paradox. It's just that the true picture is not precisely like
I see.
right panel. So because at some point the event horizon become dynamical and become time-like,
I see.
And the surface is time-like.
Yeah. Thank you. Actually, I think this problem can be stated more like in a more like clear model of anti-de Sitter space. I think there you can really take all the effects into account, and this is just an illustration. I think the upshot is that
even in ADS, I don't see. Well, in ADS, there's no there's no work on dynamical horizon as well because in ADS, I don't think you take into account the collapsing of the star and these, right?
Yeah. So, but we have other models. For example, I will show you in a moment. Actually, in ADS, even for the eternal black holes, there is a similar paradox. Like, so the event horizon, all these notions of horizons are the same thing. Yeah. But yeah, thank you for the comment. Actually, I didn't know this, but yeah.
Well, obviously, this is not the same thing because dynamical horizon. Well, the point of my question is that the dynamical horizon and event horizon is not the same thing because dynamical horizon is time-like, event horizon is not.
But I think the thermodynamical entropy will follow this decreasing curve. There is like this feature should not change. Probably you are saying like quantitatively this curve will have a different shape, but this doesn't change the fact that there is a paradox, I think.
Okay. Well.
Yeah.
All right.
Yeah. Okay. Thank you. So yeah. Also, like here I'm drawing things linearly. Actually, you should take different aspects like corrections. There are graviton corrections, probably some tiny number turbulent corrections into account. This curve, these are just for illustration purposes, I should say. Okay. And the thermodynamical entropy of the black hole given by the area, you can actually see immediately after this time, which is called page time, the radiation of the entropy of the radiation we calculate exceeds this thermodynamical entropy, which is telling you if we assume the state is pure, then the entropy of the radiation should be the same as the entropy of the black hole. These are the same, but the black hole entropy will exceed the room it can have, like for saving this entropy, for like holding these entropies. So immediately you see a paradox. The black hole just seems to have more room for these entropies. So that's the paradox already appears here across this point. And Page argued that if black hole evaporation is really unitary, we should see a curve that looks like this. Initially, you see the Hawking answer, and then after this page time, you will follow the thermodynamic entropy. So it looks like this. And this curve is the so-called Page curve. And one of the, I should say the first step in understanding the information paradox is to reproduce this Page curve, especially both for the, yes.
Now I have a question on your left panel.
Yeah.
So, sorry. So my question is what is the motivation that people say that the putrefaction of Hawking radiation start at page time? What is actually the more precise motivation argument for that? Cannot be late,
I think,
or cannot be early.
It's like this. Like before this time, like the logic is as follows. We want to see a paradox. So we want to see what is the paradox between this purity condition and like what Hawking tells you. So before this page time, the Hawking, we are assuming that this is a pure state. So okay, we can use the radiation entropy to calculate the black hole entropy. But this is not a paradox because the thermodynamical entropy is larger than that. So it's not a paradox. Like fine-grained entropy is smaller than coarse-grained entropy. That's fine. But after this, it seems that the coarse-grained entropy will be smaller than the fine-grained entropy. That's not allowed. That's a paradox. Yeah. So, does that answer your question? Yeah.
So what you're saying is that the Hawking's calculation. Okay, the Hawking's calculation is a coarse-grained entropy.
It's a fine-grained entropy. He has two versions, like the area theorem, like area over 4. That's a coarse-grained entropy. But another thing is he calculates the spectrum of radiation. That's a fine-grained entropy.
Okay, so fine-grained. So what you say is that the fine-grained entropy cannot be more than coarse-grained.
Yeah, exactly. Yes.
That is
yes, exactly.
I see.
Yes. So after this page time, you see this is the paradox. Yeah, exactly.
I see. Okay, I see. Thanks.
Okay. Yeah. Okay. So yeah, thank you. And because we need, like, it's long believed that even to reproduce these two curves, actually, because we are calculating some fine-grained entropy, which seems to need the exact quantum state. So we probably need microscopic details like UV completion, like string theory or whatever UV completion it is to understand this problem. However, last year, I think the main breakthrough is that actually, even within semi-classical gravity, you can see how to reproduce these page curves. So we have a very powerful way to calculate fine-grained entropies. The first rule is from holography, okay? So first of all, I will talk about how to reproduce this like fine-grained entropy for the black hole. For black hole, we have a rule to calculate the black hole fine-grained entropy, which is the holographic entanglement entropy formula, which is telling you if you want to know, if you have a holographic system and you want to know the entanglement entropy of a black hole, what you do is you choose the whole boundary region. Then you look for Cauchy slice where like the boundary is one of the boundary of the Cauchy slice. And then you extend into the bulk and find how can extremize this functional. I will explain it in a moment. And once you find such extremum, you just find all of the extremum and you take the minimum. This will give you the fine-grained entropy of the black hole. It's initially proposed, initially there's only this error term. This is the Ryu-Takanagi formula. And then it was argued in dynamical cases and finally generalized to include this quantum correction. The semi-classical part represents the quantum corrections for quantum fields. So this formula has a property that is very remarkable. Entanglement entropy actually for quantum fields is very famously divergent. However, it's generally believed that if you formulate this generalized entropy, for example, on any slice, for example, this slice, sigma x, it's believed that this is a finite quantity because suppose I have a boundary, my region sigma x has a boundary, then the leading UV divergence will coming from the boundary area term. And there are two area terms here. So the area divergence piece, you can think of it as a renormalization of Newton's constant, which is telling you that you can add counter terms and make this guy finite. And the most remarkable thing is in various cases, people check that this quantity is finite and does not change under RG flow. So good. And in ADS, because we're going to use holography, initially, I should say, actually, finally, I will tell you this formula has a much wider application range. And now I'm going to use this in ADS. And in ADS, there's a problem because in ADS, it's famous that we usually impose the reflective boundary condition. So ADS large black holes don't evaporate. And one of the steps that these two papers that came out last May made is we should impose a transparent boundary condition on the boundary of ADS. And then the black hole can evaporate into a so-called bath system. Okay, I will show you a more like detailed diagram for ADS, but the physical picture is just the same. And I will use the flat space-time picture here with a cutoff surface. And I sort of assume that on this cutoff surface, this formula still applies. The more elaborate model really, you can probably think of this as a simpler version of the left-hand side. So first of all, we should try to extremize this entropy, generalized entropy functional. And there's a very, the first like extremum you can find is that suppose I take the whole Cauchy slice, a fixed time slice, then you see that this guy gets extremized. And this entropy is just the entanglement entropy on this fixed background, sigma x. And you calculate this, this just gives you the Hawking answer, which grows forever. It's intuitively clear because just that, so we are now calculating the black hole, but if you think of the complement, you're collecting more and more Hawking pairs, so that's why it grows. The major breakthrough, I should say, made by these two papers last May is that actually there's another surface. So at late times, it's observed that you can have the quantum extremal surface that's very close to this event horizon. Yeah, it's not like, actually you see this surface is not literally on the event horizon, it's very close to the event horizon. But as time evolves, this interval becomes very short. So the matter entanglement entropy just becomes very small. And the entropy would be dominated by this area term. So for this quantum extremal surface, the generalized entropy will give you a curve that goes down forever. And because we need to take a minimum, so you draw these two curves, it naturally produces this page curve. I should say it's actually very interesting because we only use the information about semi-class gravity. There's no microscopic details. For example, what are the microstates of black holes? Nothing about that. But that's not the end of the story. We don't solve information paradox because information paradox, the more problematic part is why it is the page curve arises for the radiation. And let's suppose that's true for a moment. Actually,
sorry,
suppose that yes.
So I have a question. How you can determine this? Well, my question is what's the distance between this quantum extremal surface and the horizon? So how to well, how close
to calculate that?
Yeah, how to calculate how close to the horizon or how far from the horizon?
Yeah, good. It's really like the rule is as follows. So for a fixed time, I have one point on my boundary. I extend it into the bulk in arbitrary ways. And then for all these kind of surfaces, I can calculate the boundary. Suppose there is a boundary here. There is this area term. And then you can also calculate the entanglement entropy on this slice. You add these two terms, and then you really try to extremize it, which means you write this down and you see when you can, like the time direction and space-time direction reach extremum. So we really determine it dynamically. It's not, you really do calculation and you find it's close to it.
But this as semi-classical, this bulk entropy part, how you calculate that?
That's a good question. In general, like this is one of the reasons, like in the very like serious models, people consider 2D cases because in 2D these are easy to calculate. We have exact formulas for entanglement entropy. In higher dimensions, Pennington argued that in certain cases, only the two-dimensional like part is the dominant contribution, so you can still apply this formula. But that's actually a very good question. In higher dimensions, I think it's much harder to calculate this guy. But in 2D, you can actually calculate it.
All right, thank you.
Yeah, okay, good. But let's suppose for a moment that, let's suppose this is pure. What will happen? It tells you something very striking, actually. This is telling you that if this is pure, then for pure state, entanglement entropy for part is just the entanglement entropy of its complement. Then a very striking result will appear. It tells you that even if you want to consider entanglement entropy of the radiation, you have to include a part inside this gravitational region. And that's what people call the island. If you know a little bit about the entanglement wedge reconstruction, like quantum information theory, I will not dig deep into that, but I just want to comment that people believe that because this region, if you take the causal development, this is called the entanglement wedge, it is believed that any information in this entanglement wedge, you can essentially just recover by doing complicated quantum information manipulations. So this is telling you the semi-classical region inside this gravitational like red curve is actually encoded in radiation. This is really crazy. It is telling you that you can actually, although you might think okay, I just want to calculate the entropy of the radiation, but this is telling you if it's pure, and if it's pure, then you have to include this internal region, and that's really stop you from getting a paradox. And this is a formula you will speculate. And how is that actually possible? Like, because now this entangled wedge actually seems to include two disconnected regions, right? First of all, I want to tell you that this is not so crazy, because previously in our argument, the CFT is not special. Only the gravitational system is holographic. On the other hand, I can try to consider a system where the CFT itself is holographic. Then I have another direction. So suppose initially you are doing this two-dimensional problem, then you really have an emergent third direction. And if you're considering this holographic CFT, then it's not so strange, because in the doubly holographic setup, the entanglement RT surface can really end on this point, which seems disconnected from a lower dimension point of view, but they are really connected through an extra bulk. And which is telling you that if this extra CFT is holographic, then this island rule is nothing but the usual like HRT formula. And I think this is very interesting, because this is also telling you that because these two regions have a very large entanglement, they're actually secretly connected. This is really just the idea of ER equals to EPR. Okay. However, we are not satisfied, so everything here is holographic. Does it mean that I cannot solve the paradox for a non-holographic system? Actually, no.
Can you explain in more detail? So you say that although this island and radiation, they are disconnected, but somehow they are secretly connected. But but you seem to say they are connected by an extra dimension, or
yes. Because
natural, or how should I understand? But suppose you are really just considering, for example, four-dimensional 3+1 gravity Schwarzschild spacetime, so which means that they are connected in the fifth dimension. That's something in your mind.
Let's see how to say this. So remember, there is set up like this. So this system, for simplicity, let me just focus on 2 dimensions. Like you can have extra dimensions, but suppose I have these 2 dimensions. If this CFT system is itself holographic, then I have an extra radial direction coming out of the page. And
Okay, so you saying that well, but this is the gravity. That's the gravity theory located, right? I mean, your gravity theory, your quantum gravity is in these 2 dimensions.
Like if this theory, like that's why I call it doubly holographic. It's first of all the gravity theory. I have this region has a gravity, but the emergent extra dimension also has gravity in it. So I have a holography in holography setup.
Oh, is that serious? Considering Schwarzschild spacetime, but this is not. Well,
like for Schwarzschild,
I don't know if it's a holographic dual to something else, or
like in Schwarzschild, like you need holography for flat spacetime. So I don't really want to talk about it, because I'm not sure if that's a well-defined problem now.
But even for okay, so do you have some concrete some example which I mean you have a space-time with singularity with horizon as the boundary of another space-time.
Is exactly this setup. So if suppose now here I'm drawing like this is a gravity region, you should imagine there is a quantum field theory living here. Like this is my setup. If suppose my CFT itself is holographic, then I will have an extra direction, right? So CFT lives on the boundary of that extra direction. Okay. And the 2D gravity will be like living on a brane in that extra dimension theory.
Okay.
It's like the Randall syndrome type setup, I think.
Okay.
Yeah, but like this is just like historical development. Actually, you don't need it. This is just telling you. I just want to say it looks strange why there are 2 disconnected regions, but actually if the CFT itself is holographic, this rule is not really so crazy, because it's just a usual rule. Yeah.
Okay.
There's a one question from Hao Yu-san. What if the bulk CFT is not holographic?
Yeah, I will come to that just in a moment.
Okay,
in a moment. Okay. So yeah, this is not satisfying. This is a special example where this is true. But actually, then I'll come to this, which is really, actually, there's no holography needed at all. So the idea is as follows. So for a generic CFT, you should really use the replica trick to calculate the fine-grained entropy, right? So the replica trick just tells you if I want to calculate trace rho log rho, I can instead calculate this trace rho to the power of n. I'm a little bit sloppy about normalization. So, and then to calculate trace rho to the power of n, you should really go to a manifold that's multi-cover of the original manifold. And you want to do path integral on that manifold. And then you do analytic continuation, you take derivative, then you will get the fine well-known entropy. However, in our system, there's a gravity in part of the system. And when there is a gravity, we currently don't know how to do gravitational path integral, but because if you are in a semi-classical regime, you know that what you should do is you should treat other things as quantum fields. You calculate the quantum fluctuation, and then you solve the gravitational equation of motion with the back-reacted fields, and then you sum over different saddles. That's how we calculate gravitational path integral. And if I use this setup, I will illustrate here with trace rho a to the power of 2. Higher Renyi, this is called Renyi entropy, is really the same. This region inside is gravitational. So we don't have to, in gravity, what we can do is we can only fix the boundary condition, and we need to let gravity itself to decide whether whatever geometry it wants to choose. And you immediately see actually there are at least two different kind of saddles. First of all, this is the left-hand side, we call this Hawking saddle, because on each sheet, this is nothing but the Euclidean ADS. So you immediately, it's not strange that you reproduce the Hawking answer. On the other hand, there is a new saddle actually missed from all the calculations, and it's really a saddle. I should repeat it. It's just very hard to calculate actually, but that connects different sheets. Like for this chosen boundary condition, there is a natural gravitational system, a solution that connects different sheets. And by doing this path integral, I really need to sum over all the terms. Okay, and when we usually talk about the gravitational path integral, we choose the dominant term, which is the largest term. So you immediately see that when these two terms, when I have these two terms, it's actually possible for these two guys to switch dominance. Okay, and it exactly happens because you should think of this term actually it's roughly speaking e to the minus entropy. So when entropy is large, this guy is much like very greatly suppressed. So I will be dominated by the second term. So which is telling you that in my gravitational path integral, if I honestly do gravitational path integral, I should also include the second term. And for high Renyi, this is shown here. These kind of solutions are called replica wormholes. And this really tells you that this island formula is derived. So let me restate this again. Why is there an externalization procedure here? Because I'm calculating gravitational path integral. For gravitational path integral, you need to solve equation of motions, which is the extremum of the gravitational action. Okay, this is the reason why there is extremum here. And the minimality condition is telling you that you should take the largest term in this trace rho to the power of n. So,
can I ask a question?
Yes.
So like in your CFT part, when the connected saddle is dominant, so you think your CFT lives on the connected drum-like basis, right?
Yes, yes.
Thanks.
Yeah.
So these calculation is like, I mean, it seemed to me that it's like you assuming the result, right? And this is like you assume you have topological change, and then you get island formula. Right? And
that's a good question, actually. I think this is a common objection, but it's really, if you let me see how to say this. It's really the rule we propose for Euclidean path integral, I should say. Like when you do path integral, you should include all the topology change.
Well, I mean, there are many path integral of gravity which do not need topological change, but most of them are of course in Lorentzian signature. But okay.
Yeah, there are two things here. First of all, this is Euclidean path integral. So the second thing is, I think the upshot is this: if usually the first term is the dominant saddle. So usually, even if you only include this term, it gives you the correct answer because this is the largest term. But when you see a paradox, actually you should question whether we're really honestly doing the rule Euclidean path integral tell you to do.
Okay, but you said yeah, I didn't know it is a common objection. So I had this objection, but I didn't know it is a common objection. So it is a common objection. What people usually reply for this common objection? So
the
like
objection is this: like gravitational path integral, Euclidean gravitational path integral is actually not well defined because there is a negative mode, so it's not bounded from below. Yeah. But Hawking and proposed, at least Hawking, Page, those people proposed that in understanding the path integral, because now we don't know how to do exact path integral, so we should just include all the saddle points, including all the different topologies.
Yeah, it can be also imaginary saddle as well. It can be.
These ones are actually they are complex saddles actually. Yeah.
Yeah, there are complex saddles, and on those complex saddles, and these exponential are actually auxiliary.
Yes, but you also have a norm term, right? Norm part. They are not imaginary saddles; they are complex saddles.
They are what? They are
complex saddles. They are not
So for those complex saddles, but the action become complex, right? The action will become complex, and probably they are going to be purely imaginary. Some of them may be purely imaginary, right? Then the exponential become auxiliary. And then it actually affect your leading saddle, your wormhole saddle. Because
this is a good question. Yes, you can actually really calculate these terms, and you found that the phenomenon you said is true. That's why the second term is not always dominant. It is really they switch dominance at a certain point.
I see. Okay.
Yeah. So yeah. So
can I ask you a question?
Yes.
How did you calculate this Euclidean path integral with a replica trick? You need to impose a twisted boundary condition here, right?
Yeah.
And do you know? I'm not sure if you know twisted operator in higher dimension other than d = 2.
Yeah, that's a very good question. I think the replica wormhole, the papers I cite here, they only deal with 2 dimensions. There are some speculations in higher dimensions, but yeah, let's be a little bit conservative here. I don't know actually. Yeah, but these derivations are working 2 dimensions.
Thanks.
Yeah. Okay. Yeah, just to be clear, actually, let me just show you. So if you follow this rule, if you believe my derivation, then this is telling you that we should extremize this functional and take the minimum. So it actually is really, at early times, this saddle where there's no topology change, it's the usual, you just include this part, is the dominant contribution. That's why initially it grows. And then at late times, the dominant one becomes this one. So this reproduces the page curve. And I have some comments on this formula actually. You might feel actually pretty strange because R appears both left and right. I want to stress this point. It's a little bit confusing if you see this for the first time. On the left-hand side, we believe we are having the, suppose now I really have the exact quantum state for rho R. I can just calculate minus trace rho log rho. On the other hand, on the right-hand side, I also have some R, but this S method term is on fixed background. So we are using semi-classical gravity. We get a formula on the right-hand side where there's only semi-classical gravity answers, but the left-hand side, we expect it to approximate the exact answer. Also, I should say that these 2 terms are really competing each other because whenever I have a boundary, say I have this I, which extends here, I should really pick up a new term. So it makes this term actually become larger. But in these kind of situations, where there is a large entanglement between the radiation and inside, the price I pay for this area is really much economical than this reducing this entropy where I have both region I and region R. So this is sort of the mechanism why it's actually lowered this entropy down. So I should stress this again. This is a formula not relying on holography at all. Now, and we believe this is the formula. Yes, yes.
Can you remind me how, in what way that when you include these additional replica wormhole saddles, and then you take the replica limit and goes to 1, that replica limit give you the island formula? Like, what are the missing steps in between? So I see these replica wormhole saddles arising, but how do I see that these replica wormholes will give you the island correction to the original, say the RT formula, when you take the replica limit?
Good. The idea is as follows. So these replica wormholes, they are replica symmetric. So an easy way to analyze it is to take a quotient. When you take the quotient, you will see in the gravitational region, there will be emergent twist points. So that's why in the calculation of entropy, you need to include an extra piece. Does that answer your question?
Okay. Okay.
I have a related question. So sometimes we will talk about having islands behind the horizon. Is that correct? But in the Euclidean calculation, I can't really see behind the horizon. So I'm always confused about those statements.
Okay, good. The reason why, like, are you worried that Euclidean geometry just doesn't include things that's behind the horizon?
That's right. So how do I see that the islands showing up in the island formula is the same thing as this? It is very related to the question of Huajia, specifically, if the islands are behind the horizon, in what sense they came from these replica wormholes?
The solutions are complex. In Euclidean calculation, yeah.
Oh, you mean the geometry is complex?
Yes.
Okay.
Like it's drawn in this intuitive way, but actually, you're right. In order to see them, when you continue to Lorentzian signature, actually there are Lorentzian evaluation. Like, yeah.
Okay, so the cases where the islands fall behind the horizon should correspond to some complex geometry.
Yeah. Yes. Okay. Yeah. Oh, I assume I answered your question. So,
sorry, the complex. So you mean when you look at those saddles of basically solving equation motion, you are actually getting the dominant contribution to your path integral is actually a complex geometry. That's what you say, which is the original Lorentzian geometry. What you are supposed to look at.
There are both Lorentzian part and Euclidean part.
So you are going to take into account two saddles, and one is Lorentzian, which was the original geometry, and the other is the Euclidean continuation. That's
not quite. Like in the solution, actually, it's a combination of Euclidean and Lorentzian. And I should really say, although I draw them here, the solution for arbitrary n is really complicated, and up to now, nobody really knows what is the exact solution to them. And we can only do analysis where n approaches 1, because that's, so for Renyi, we don't have an answer. For entanglement entropy, we only need the leading n-1 contribution. So, and that's what gives you the island formula.
Oh, do you mean that in the n-to-1 limit, then I can look into perturbation even of the Lorentzian geometry, introducing a little singularity in the Lorentzian geometry?
Exactly. It's very similar to the Leukevis-Melder calculation. Yeah.
Sorry, I still confused. So you say it is a combination between the final dominant contribution of the saddle is not a Euclidean. It is a combination between Euclidean and Lorentzian. Is that signature change in the spacetime, or what is exactly the spacetime structure for the saddle?
Like for n,
or you have two saddles, or you only have a single saddle?
A single saddle where there is Lorentzian and Euclidean like signature in the. So I should really say, sorry.
In the signature change in the space-time. Like a Euclidean geometry glued to a Lorentzian geometry.
Or I should say probably like follows. You see, there are the solution. Like, let's see. If I take the quotient, I have the twist point. I need to know the position of the twist point, and the solution for the time is really complex.
Okay.
So is it true that the solution, the saddle point solution is complex because you are extremizing it with respect to adding contribution from the entanglement entropy piece? Like why are the as you mentioned the saddle point geometry that correspond to these Euclidean wormholes, they are complex? Is it because they're complex because you need to extremize by adding additional contribution from the entanglement entropy part that force them to fall behind the horizon? Like, what is a dynamical reason that these geometries, the optimal geometries are actually complex geometries?
I don't have actually I don't have a very intuitive answer. I should just say, like, when you solve the back-directed equation motion, it turns out to be the case. And actually for n larger than 1, people are not able to solve it currently. So yeah, I don't have a good intuition for that.
Can you give us an example, maybe at the end of the talk, just one simple example of the form of the geometry? Then we have some idea of what's going on. Doesn't have to be now, after the talk, can you give us an example? Then it's easier for us to imagine.
It's actually, I think it's not so easy because, as I said, again, like for arbitrary n, nobody really knows the answer to that.
So here, basically what you are doing is you are using the replica wormhole to derive the island formula. And that's all these replica wormholes does to this part of the story. And then you are just using the island formula and just extend it to Euclidean signature and do the extremizations.
Exactly.
I see.
Yeah, so yeah, exactly. Any other questions? Okay, I guess I can go on. So,
sorry, there's one question by Hao Yu-san. What is the relation between this Euclidean complex saddle and the EOW brain, end of world brain in the Euclidean signature? That's the question.
In this model, I'm basically following the story by this first paper. In this model, there's no end of world brain. I guess you're imagining like the Stanford group story. Yeah, I don't have a very intuitive explanation how to connect these two models, so I just I don't know.
Okay.
Still ask a very simple question about CFT path. I originally thought the CFT live on the plane that are attached at the ends of the drum, but you say the CFT actually lives on the drum, connected drum itself. So it seems there's a drastic change when the saddle changes. But in the Lorentzian picture, the CFT seems always live on the attached flat places, and I couldn't see that the geometry of the CFT changed drastically. So I don't know
that's actually true. This is true. Like, this is a feature of Euclidean path integral, I should say. You cannot just literally continue this back to Lorentzian signature. There are similarities, and let's see how to say this. It's like, for example, when you see instantons, you only see them in Euclidean signature. It's not clear what they mean in Lorentzian signature, right? It's just a way of calculating this path integral, I should say.
So you actually really calculate the entropy of CFT on this connected piece rather than on the plane attached at both ends?
On the plane attached at both ends. Let's see. Yeah, this is what you would do if you want to use replica to calculate entanglement entropy, right?
Maybe I can ask you later, but I don't think what you are saying is intuitive to me.
Yeah, we can talk about it later.
Thank you.
Yeah. So any other questions? Because I'm essentially done with this review part.
So I have a question. So what people think, including you and your collaborators, and what do you think about the real physical mechanism that why those Hawking pairs falling into singularity can putrefy the radiation?
This is a very, very good question, actually. I want to stress this. This is not the solution of the information paradox. I should say we are only not able to reproduce the page curve. The dynamical reason, there are arguments, like Hong Liu have an argument saying that for generic chaotic systems, this will happen. But I think now nobody really knows what it means in a Lorentzian dynamical procedure, how information get out, and what's really like the corrections to the density matrix, for example. Yeah. So instead, I should say we have a formula for the fine-grained entropy of a system coupled to gravity. That's what this calculation does, I think.
Okay, and then
yeah.
Okay, so second question is, so how does the scrambling and chaos play a role here? Does it play any role in this?
Good. Yeah, that's a very Lorentzian question, right? So
that's right. Yes.
I think
some intuition relates to this.
Yeah, these papers don't address this point, but I think Hong Liu recently has some nice papers. People are trying hard, and they have some like toy models for explaining what, like as you said, scrambling, quantum chaos. What's how the role played here? Is it generic, not only for black hole? How dynamically information come out? Something like that. But it's not really what this calculation can answer, I think.
So if I were to some sort of so is it right to say that the fact that the interior of the black hole purified the radiation outside is something suggested by the replica computation? Is that a fair statement? That what?
I think so. To really argue that, you need to assume entanglement wedge reconstruction, right?
Right.
Because yeah, if you use that to argue, then that's correct. Although I don't know that, we don't know the dynamical procedure that make it possible, but it seems that this is the answer, I think.
Okay, so wait.
Okay, so I assume no questions. Okay, let me go on. So a very natural question to ask is this island story only exist in black holes? And if not, actually, how do we find islands? What are the situations where a region in space-time can be actually encoded in something else? And I want to stress this because in the later part of the talk, you might get confused. The island formula tells you how to calculate the fine-grained entropy for a system in a non-dynamical gravity region coupled to degree of freedom that's living inside gravity. However, we want to ask a question that turns this around. We want to ask, is it actually possible for any region I to be an island of something else? Okay, it might be like a bit confusing, but I think I will make it clear. Okay, so really now let's talk about the main part of our work, this paper, which is the quantum information constraints on the islands. So first of all, I want to provide you some intuition why a very toy tensor network, a picture on the first condition we will derive, which is the violation of the Bekenstein area bound. So it's noticed by Brian Swingle that if we have a tensor network, these legs, external legs represent the state, and the bound connecting different regions represent entanglement. So for example, in this diagram, the entanglement between I and G are provided by the area. And for I and R, they are provided by Hawking radiation, okay? So dynamically, you can think of like, first of all, if I go to late times, I will have more and more radiation because Hawking radiation come out. And also the area of the horizon decreases, right? And the tensor network tells you that if you want to calculate the von Neumann entropy of a quantum state, then you should try to find a way to cut this part out from the rest of the diagram and find the minimal length for the cut. So at early time, this is the most economic way because there are not much Hawking radiation coming out. On the other hand, when Hawking radiation becoming more and more, there's another cut, like the cut here. And this is just the island formula, right? And also, it sort of answers Jan's question because these two regions, you can have very complicated like quantum channels to get information for island I from manipulation this region R. And I should say, I think this is really the motivation of the Pennington work, why he suspects that there is another quantum extremal surface. So let me pause here if this is clear.
So what do these letters represent?
Oh, sorry. You should look at the diagram on the right-hand side. So they just represent, yeah.
Okay.
Yeah, I should say that, sorry. Yeah, I should say this is a very toy like model, and recently there are papers having much better models, probably even including dynamics, but I think this is really the physics behind it. And it's actually very interesting, yes.
The reason to separate into G and B. So I is island, R is radiation. So what separates G and B?
Good. So I'm using, there are several reasons why I have this G and B. I should say it's arbitrary because G and B just represent the two parts like cut by this cutoff surface. It's sort of arbitrary where you decide that gravity is weak. We put it here because, yes.
So G is the gravitational region and B is somehow not gravitational.
Yeah, exactly. You want to turn it off, yes. Here, it's sort of arbitrary. You have to assume somewhere the gravity become weak, but in our FRW model, actually, it would be clear because there are separatist spacetimes, so there is no confusion. Here, it's just for like, I want to use those diagrams. Also, I want to like make connections to what we will do. So I do it like this. Yeah.
I see.
Yeah. Okay. I assume I can go on. So the first condition is really just the entanglement entropy of any region in spacetime. The island entanglement entropy should be larger than the area of its boundary. Okay. So I will explain what this hat means and what this twiddle means. So the idea is as follows. So roughly speaking, because the island formula tells you that once you find multiple extremum, you should take the minimum. So suppose now I find one with island. If I want it to dominate, it must be smaller than the entropy without including any island. Okay, so then you can remassage the terms, move some term to the left, some term to the right, and then add, subtract some terms. Then you get this. The right-hand side is literally the Araki-Lee inequality. So are we done? Is it telling you that the left-hand side is positive? Actually, not quite, because that's why we like explicitly write these counter terms here. You can actually see the left-hand side, right-hand side are, this inequality is just trivial because there are UV divergences. But it's actually not that bad because you can actually use a more elaborate argument. If I have time and anyone is interested, I can show you more details. But the rough idea is as follows. So I denote this hat by the finite part. I subtract the common term, I get a finite piece. And using monotonicity of mutual information and this so-called mutual information regulator, what I really get is this inequality. And I have, in this inequality, I have a part that's a finite entanglement entropy in this tiny region C. This tiny, well, this finite part, the finite part looks like this. It looks like divergence, but actually it's not. Delta is a physical distance instead of a cutoff. And if I choose it to be much larger than my cutoff and also larger than the Planck scale, I can just throw it away because then this term will be much smaller than the first term because delta is much smaller than the Planck scale. So that's why we get this final answer, which is telling you that the finite part, is greater or larger than area. And I should stress that because of the assumptions we made here, we should really just take seriously the extensive piece of the left-hand side. Yes. Is there a question? Okay. So this actually is one of our motivation for looking for islands in cosmology. Because in the previous black hole example, we see the island can exist when there is a large matter entanglement, and also you have to pay not so large cost for the area. In FRW, for example, the entropy density is a constant. That's just the adiabatic approximation. And then for any fixed region I, with a boundary, I will have the entropy, that's the thermodynamical entropy, the finite part, sigma times its volume. And the area, I would multiply this scale factor. The difference is really the entropy is constant in cold moving volume. Instead, the area is really the physical area. Okay. So because of this A here, the bound can very easily be violated. Suppose, for example, I have this radiation dominated FRW. When I go approach the singularity, this A will be very close to 0. So this bound will be very easy to violate. The right-hand side will be almost 0. So it's very easy to violate that. And it's very natural to ask, so does this suggest that any region, as long as it takes close to where A is small, it can be an island? Actually, not quite, because remember, this is only the minimality condition. We also have the extremal condition, and that's our condition 2 and 3. I will describe in a moment. And I should mention that recently there is a huge interest in this subject, finding islands in cosmology, and there are various interesting papers coming out. And especially this Princeton group, Chen, Gobento, and Maldacena paper has a very, the conclusion is very similar, and I will show you actually, the starting point is different. So I will show you, after I describe our model, what are the connection differences between those papers. Okay, so I told you it's not enough. So what is the second condition? The second condition is it really have to be an extremum. I'm using terminology invented by Engelhard and a Berkeley group, a paper called quantum maximum surfaces. So they call this entropy the hybrid entropy because it involves both something in gravitational region and non-gravitational region. We want to extremize this by deforming in the gravitational region. So if I expand it out, there are these 3 terms, and I can remassage these terms because, as I said, we want conditions purely on region I. These island formulas always include this region R, so I want to separate it out. And it's very interesting, actually, when you separate it out and add a term that's not related, like it doesn't change under this derivative, then you see you can rewrite this condition as the generalized entropy of this region I, which is a UV finite quantity, is equal to the derivative of the mutual information between I and R. Both sides are finite quantities, I should say. And the left-hand side is purely related to region R, I. No R is involved. And there is a, and the right-hand side actually has a definite sign because when I deform it a little bit, I can write it as this I prime, mutual information between I prime and R and I and R. And when subtract the two, it must be positive. This is, well, there are multiple names for this. It's called positivity of conditional mutual information. It's called monotonicity of mutual information and the inclusion. And finally, it's actually just application of strong subadditivity. But this has a definite sign under null deformation going in this positive direction. When you consider negative direction, it flips sign. So finally, what you get is this condition. Because these two are equal, so the left-hand side should also have this sign constraint, which is telling you that the derivative in the null direction, when you go in outgoing direction, is positive. In the ingoing direction, is negative. We call this quantum normal condition. Because very interestingly, this null derivative is proportional to something called quantum expansion that's introduced by the Berkeley group. So essentially, these conditions are telling you that I use this Fermi theta plus minus and plus notation. This is invented by Bousseau. I use it here as well because I want to make some connections to the classical version. So these are just telling you wherever you, whether you deform it in future or past, As long as you go outward, the area of the surface increases. As long as you go inward, the area decreases. I said area, but actually it's the generalized entropy, which is area plus its quantum correction. Suppose now I really throw away the quantum correction. You will see immediately why it's called quantum normal, because in that case, I dropped the entanglement entropy piece. So this is just a classical expansion. Okay, classical expansion, positive just tells you when you go outside, the area becomes larger. When you go inside, the area becomes smaller. So it's very normal to call this surface normal. So we call this quantum normal because it includes the quantum correction. And okay, are there any questions so far?
Just a quick question.
Yes, yes.
So in this case, I guess you assume the boundary of the island is always inside the horizon, right?
Actually, no. Like this is just for like this is what really happens. But I'm just about to tell you, island's endpoint can outside the horizon, and it must be outside the horizon.
Okay. Thank you.
Yeah. Okay. Yeah. Let's just go there. Actually, this is a very interesting application, I think. So it is found that for eternal black holes, the islands are always outside the horizon. And the reason is that, well, it's initially noticed by this paper. There are actually other papers I didn't cite that also found this phenomenon. It's really just because of this condition too. Because suppose now I consider this island, I want to see where this island endpoint can land. And I know that it must land in the so-called quantum normal region. By Booth symmetry, I know that along this curve, the derivative is 0. So the derivative, I can only really land on one side of this this horizon region. And I draw the blue region is the quantum normal region. I'm using the notation where Boussel used. So there's a wedge here. This is called Boussel wedge. So the direction it points is in which direction the quantum expansion decreases. So for example, if I'm in the above patch, it's because this is a trap surface, so it only the quantum expansion is negative in the future inward outward direction, and for downward it's reflected. On the other hand, it's really in the right patch that is quantum normal, so only inward directions can give you negative quantum expansion. So you immediately see that the island endpoint can only land in this patch, which is actually the reason why the islands are always out. That paper is called Island Outside the Horizon. This is, I think, there are explanations from high dimensions, but I think from a lower dimension point of view, this is really the first explanation why this must be the case. So any questions so far?
But in case the island is outside horizon, then how it relates to
so what do you mean by, sorry, so what do you mean by quantum apparent horizon here? It just means that the quantum trapped, I mean the surface defined by the quantum expansion?
Yes,
there
has 0 derivative. Like quantum expansion is 0.
So in the sense, only if the quantum horizon and the event horizon are different, then you have a chance of the island.
Actually. Exactly. That's why I think in these stories, quantum corrections are so important. Yes, exactly. Actually.
As you saw, in the evaporating case, you can actually check that the quantum, or quote unquote, quantum horizon is actually, the thing still lies outside of the quantum horizon, but it's inside the classical horizon.
Yes, exactly. Actually, the classical horizon is outside the event horizon, and the quantum horizon is inside.
I see.
Yeah.
Interesting.
So, yeah, any other questions? Okay. So, actually, like previously, we sort of provided a lower bound. It's not surprising there's an upper bound. So the third condition, we call it G is quantum normal. So the idea is similar. You use quantum information inequalities, for example, strong subjectivity. You write it like this. And G is a region that shares the boundary with I and its surrounding region I. Because they have the same boundary, so the area term is the same. So you can actually rewrite it like this. So, so just to compare, the previous case with the previous case, the difference is really just the sign flips. And it's actually also very intuitive because the inside-outside means different things for these two regions, right? For if you deform in this direction, for I it's outside, for G is inside. And like I also include this diagram here for W. Okay, so let me make some comments for these three conditions.
Sorry. Before going,
yes,
there is one comment,
yes.
one question in the chat. Hong Wentan from Hong Wentan asking, classically, the island should be the inside the horizon. That's the question.
Can you say it again?
Classically, the island should the island be inside the horizon?
Classically, there is no island, right? So
okay.
I guess probably the question is like this. Well, here I don't show you the diagram. For evaporating black hole, the classical apparent horizon lies outside the horizon, and the quantum apparent horizon lies inside the horizon, and that allows you like to like it should be outside the quantum apparent horizon. That's why actually it's not a contradiction that the island is inside the horizon, event horizon for evaporating black holes.
Okay, thanks.
Yeah. Okay. So yeah, just as what Haja asked, I think we should at least reproduce the classical answer. It's actually very interesting. You can still remassage the terms like this into one inequality, look like this. And in the classical limits, the left-hand side, right-hand side has a GH bar in it. I send it to 0. So left-hand side, right-hand side, both 0. It's just telling you that it just gives you the classical HRT extremality condition. And it's really the quantum correction that enlarge this position into a codimension 1 surface. And that's where island can land. Okay. And I want to stress that the philosophy is sort of flipped here. You will see this in an example. These conditions only give you restrictions on region I. Nothing is about region R. So what we are asking is this question. Let me stress this again. For a region I with a quantum state, is it possible for this to be an island of something else for a region R, for example? And of course, we checked all existing islands satisfy these conditions. And one more funny thing is that so you might ask, can we actually play this game with more derivatives? Yes, actually, yes. You can take one more derivative with respect to the position of R, and combining with quantum focusing conjecture, it actually tells you that the extremum must be a maximum. What does that mean? This is a word invented by Pennington, no, by Engelhardt and Bohr, actually. So this condition tells you that when you do the extremization, so finally, extremum can only exist for a maximum in time and a minimum in space. And it's actually very interesting. We will see this condition, this maximum condition has a very interesting connection to the quantum non-energy condition. Yeah. So yeah, we will see this in the explicit example. So
if I understand it correctly, all those conditions only work for the entire state is pure, right? I mean, black hole plus radiation is pure. If I consider general a given initial mixed state, all this will not work.
Actually, no. Like I should say, the question is really this: suppose I give you this FRW spacetime. It's clear that this state is not pure, right? But you can find, the question is sort of, can you find a purification such that this guy become an island?
Yeah, I mean your entire Cauchy-sized quantum state. Do you assume it's pure or in general can be mixed?
In our derivation, we didn't assume it, but in the examples I'm considering, I think all of the complete Cauchy states are pure.
Okay, thank you.
Yeah, like actually in some of the steps in the derivation, we even include a purification. So if it's not pure, you just include a pure, like an extra piece that purifies it. So in the derivation, I should say like it's not required. Yeah,
okay,
does that answer? Yeah, okay. Okay, so we're kind of bored with stated a lot on our conditions and reviews. So now let's really look at examples. The first example is the one I just described to you, FRW universe. So to make the setup clear, let me state it again. The spacetime in FRW universe is given by this, and you need to solve the Einstein equation or the Friedmann equation to get what the scale factor really is. And there are these two kind of convenient coordinate choices. One is with time t, one is the conformal time eta, and yeah, okay. And the quantum state we are considering here is the thermofield double state. You might feel that, well, in cosmology, it's usually assumed that it's thermal, but we're actually making a stronger assumption than the usual cases, because usually it's thermal on a larger scale, but we are assuming microscopically it's pure. It's thermal, sorry. So we can purify it with another auxiliary system, which using the thermofield double construction, which is we do Euclidean path integral with these two time equal to 0 slices as endpoints, and this produces this state. Then we do a conformal transformation on one of the parts to make it FRW, because these two spacetimes are conformally related. Okay, so and there is a simple reason why condition 1 will tell you that this kind of thermofield double will also kind of have an island. I'm just presenting to you the simple toy tensor network picture again, but it's really the same thing as the black hole case, because in this situation, the entropy comes from different things. First of all, the matter entropy now comes from the thermofield double state we choose, and the entanglement, the area term changes because we have the scale factor, not because it evaporates. So it's natural to expect, oh, now I calculate the entropy of region R. Is it the same story? Do we always have an island as previously suggested? Actually, no. So let me just show you. The first simplest example you will consider is the radiation dominated FRW. So this is the solution. And when we consider radiation only spacetime, we have these relations, and you can calculate the generalized entropy to be this quantity here, and you can check various conditions. What about, well, let me state this again. I only look at a patch where region I lives. Region R does not matter, because when I check the three conditions, how you purify it does not matter at all. Okay, and the three conditions are shown here. The first condition, the Bekenstein violation, has this is inside this blue shaped region. And the I quantum normal is this, actually it's just the, this like dark bluish region. And G quantum normal region, the condition is never satisfied. So you know that whatever you do to purify this system, in a thermal state, you are never going to make any regions as an island. So this is purely for radiation domination. You can ask, what if I want to ask cosmological constant? So first thing we try is we add positive cosmological constant. Nothing really much changes. You just sort of tilt this diagram a little bit, and you see, because now there's a de Sitter part. So you need to tilt this diagram, and it really doesn't change much. And you know that it's impossible because there is no overlap between these three conditions. And simply from these conditions, we know it's actually impossible for region I to be islands for anything else. But well, just for sanity check, you can actually just check that suppose I really want to use the thermofield double and I choose a region R like this. Are there any R's that this I can be an island? And to calculate that, I need to know two more things. The first of all is I need to know a two interval entanglement entropy calculation across the thermofield double. And the second thing is it possible to extremate that? And let me actually show you a little bit. This is calculated by these authors here. There are a bunch of papers like especially studying quantum crunch, a lot of literature. And the general structure of the entanglement entropy across the thermofield double can be understood using this quasi-particle picture. So to calculate entanglement entropy on two sides, you essentially just count how many quasi-particle pairs are included in these regions. And the reason why it works is essentially just because we prepared this state by a Euclidean path integral. And so you expect that the entanglement spectrum is local. So on scales much larger than beta, the entanglement is really local for the state you prepare. And in general, I should say here, the formulas for equal time, equal space is sort of easy to derive. But in general, if both of them are non-zero, it's really a very complicated function, a complicated expression with a function f unknown, and which depends on theory. Okay. And there are some general properties that I will show you, but yeah, that's the essential picture of this quantity. Then you can just the next step you will ask is previously as described to Minkowski. Excuse me. So now, if I turn on the scale factor, actually what I do, I don't change much. The only thing that changes is the cutoff will become the physical cutoff. So the finite part will, the divergent part doesn't matter. Like as we argue, it will be absorbed into normalization, but the finite part obtain this extra piece coming from logarithmic divergences. Okay, that's it. This is the formula, and you can try to extremize it. Yeah, we don't know this function f. Fortunately, in this case, when you try to take derivative, you see that one of the derivative condition is never satisfied, because although this function is unknown, but there is a speed limit derived by Tom and Nima, which makes this derivative condition, like it makes it impossible to extremize this function. Okay, so this is a story for radiation domination. On the other hand, the real hero in our story is really, what if I turn on negative cosmological constant? There, surprisingly, there is an analytic solution for the Friedmann equation, which look like this. And in this case, the three conditions are not all trivial, or I should say they actually do have overlaps. So you see, I draw like the same colors for Bekenstein bound area bound violation, I quantum normal, and this G quantum normal region now is not trivial. There is this tiny region here, and the triple overlap here is where the island can land. It's a triple overlap of these conditions. And I should say, it's really, really very restrictive. We sort of draw this diagram, exaggerate a little bit, but the scale of this triple overlap is just a thermal scale. It's thermal scale beta, much smaller than the region we are going to consider. So good. Okay, now we say that our logic is, okay, I told you that in this region, it's possible that these points can be islands for something else. Are they really islands of something else? So let's try to really find islands. So when we really try to find it, I need the auxiliary system. I want to generalize the entropy with this R, again, as previous case. And I will briefly mention how we can do it. So first of all, the easiest thing to try is, now I have a lot of degree, like freedom here. I first put my region R almost at the origin, or smaller than this thermal scale. I try to extremize this functional. Now we face the same problem. This F is theory dependent. Like this A become a more complicated function, and this F is theory dependent. However, there are some general properties of these functions, because we know that they are going to be linear when, excuse me, when the, let's see how to say this, when they are much larger than the thermal scale. So you can actually check that just by linear assumption, although the explicit shape depends on theory, but they all have this kind of behavior, which is it first go up, then go down, and it has some maximum around the origin. But as I said, because of the assumptions, because of the conditions used here, you can only trust this behavior outside this this like bracket here, and so at least we know here there is an extremum. In some cases, we can do better. So in our current case, we're assuming that this delta is like, we know that island must land on close to the turning point, and also the region R is very close to time 0. So this delta eta is actually, if it exists, I just argue that it must be much smaller than the thermal scale. In this region, it's also universal, although the constant is not universal. It's universal in the sense that the entropy function f must be quadratic. And we plug it in, you see it's very interesting. I just argue that the quantum focusing conjecture will tell you that it must be a maximum, which tells you, at least in the time direction, it must be a maximum. And it is only a maximum if this BF satisfies this condition. Interestingly, this bound was previously derived by Mazet and Varela using quantum non-energy condition. So it's probably not so surprising that I use quantum focusing, so you get something related to quantum non-energy condition, but I just say these two are really independent, and one does not come from the other here. Okay. So, okay, then you can ask the question, suppose I'm not satisfied for putting R here. What if I want to move R above? You can also find islands. In this case, it's much harder because the formulas are really like the generic behaviors in the regime that we talked about is really not enough. I really need to know more for this region. So instead of looking at general CFTs, we use the holographic formula, which looks like this. I don't need to know much detail about it, but it just tell you that if you extremize this functional, you see there is a maximum surface, island surface here. And one interesting thing we find is actually, whatever this region R is, this island region must be inside the butterfly cone of this region R. So the region R endpoint shoot out a butterfly cone, and the island region must land, the endpoint must land between this point and the same position where R ends. Okay, so yeah, are there any questions? Actually, I want to provide a sort of like these. I don't have much details here, but I hope it's clear, and I will provide you actually why intuitively that must be a case island must be there. So any questions? I think this is a good point to ask question. Oh, I assume there is no question. Okay, good. So actually now I want to explain to you why actually our island must land in this tiny region. There is a very intuitive reason for that. So the reason is as follows. I explained to you that there are these two terms here. When we include, actually the matter term want to include everything that's highly entangled with region R to make this term minimum. On the other hand, the area term, when you include those kind of regions, the area term will like, you will include an extra area term, and these two terms compete with each other. On the other hand, this is the first condition. The second condition and third condition tells you that the derivative must balance, okay? And for radiation only FRW, when you take derivative, you see that the area term, the derivative of the area term is much, much larger than the matter entropy term. So it never balance, there is never a balance between these two terms. On the other hand, for the recollapsing case, around the turning point, the scale factor derivative is 0. So there is really a chance for these two terms to balance. And because of this condition, we know that it must be very close to the turning point. Because of the first condition, I know I should include as much region as highly entangled with R as possible. So finally, we roughly just include everything with the same size and at time 0. That's this picture here. That's the intuitive explanation why that's the case. And you see it's actually very beautifully captured by our conditions. It's only this tiny piece that is possible for them to be all met at the same time.
Oh,
so any questions? Yes.
But why should the butterfly velocity shows up in this calculation?
Ah, good. The reason is as follows. Suppose I'm in a smaller region, I here, then you see the entanglement between I and R, it was like, let's see, when you use a quasi-particle picture, this like, the entanglement just can't spread outside the butterfly cone, right?
But what about the entanglement velocity? So somehow
good. Like it's actually very interesting. We also thought initially it's probably the entanglement velocity cone, but when you try to extremize it, you see that you see in this formula there is this VE and this VB, right? And let me see how to say this. If you want this formula to be how to say this? It's not like delta R is not really zero between these 2 points, you see. So this guy will contribute a term here, and a special combination between VE and the denominator will give you VB. Yeah, Janet?
Yes.
I think actually,
right.
Yes.
That somehow it would show up in that combination.
Let's see how to say this. If you plug in formulas, first of all, I should tell you this function is only smooth if VB and VE have a special relation.
Oh.
And that's really the yeah. I don't have a very good answer to that. It's sort of magically popped out, I should say.
Okay. But
I can yeah.
But
yes.
there's some subtlety that is not completely clear yet. But anyway, yeah.
It's not trivial. Yeah, and we don't I don't have a physical reason why that's the case.
Okay, thanks.
Yeah. Okay, so I think many of you might be interested. We actually, the setup looks, if you read their paper, we have 2 models here. Although they don't consider 4 dimensions, but they have a very similar setup. So I want to explain to you what's the difference with the Princeton group paper. So in our setup, we sort of look at the thermofield double state, which is prepared by this Euclidean passing rule on a chosen background. I choose to consider this background that prepares this state. On the other hand, what they did is they prepared this state by Euclidean path integral. Again, as I said, in Euclidean path integral, you're only allowed to fix boundary conditions. You cannot determine what, you cannot fix a background. So if you prepare the state using this, you should let gravity itself to choose what state it wants give you the dominant contribution. And what they found is that the setup is as follows. So the state is, they consider a state living in this like flat space, flat slice, and there's a dynamical gravity region. And you found that when you consider the bra and the cat, the dominant geometry connects these 2. And if you cut it from the middle, it's really giving us our setup. So I would say in our setup, we decide to look at cosmology, which we choose a specific state, but they choose a state that's prepared by Euclidean path integral, and it's emergent, sort of. The cosmology is emergent, and the gravity knows that it should pick this saddle. If you don't pick it, there are some paradoxes. That's one of the things that they described in their paper. So is this clear? Okay. So finally, okay, yeah. So I should probably be brief on this 1+1 dimension model. So in 2-dimensional JT gravity, there is a de Sitter solution that look like this. I should say actually 2D de Sitter is sort of special, and especially the solution here, if you view it from dimension reduction, it's really just the dimension reduction of high dimensional de Sitter-Schwarzschild black hole. So although we are sort of viewing it as a cosmological model, but from high dimension point of view, it's really just a black hole. But what I want to show you, yeah, it's actually very interesting that in the Princeton paper, the latter part is describing these models. So what's new in our formalism is that we study these overlap of quantum, our 3 conditions, and actually it's much more strict than you might thought. So there are different parameters you can choose for the theory. So if you are in this regime, you can see there is a tiny overlap, and the island is here. indeed, we find island and they find island land in this region. And if we are in this regime, it's actually much more restrict. You can almost pinpoint the island endpoint position to a single point, and that's really where the island lands. So kind of funny. And as I said, these conditions, we only applied it to region I. So next we find different realization of island with a chosen region R. The first way is I put the region R near square plus here, so which is a non-gravitational region, and indeed you find this is the island. And then another thing you can do is just like what you do in ADS, you glue it to a flat space bubble. Again, you find that this kind of region will give you an island almost in the same position because our condition sort of restricted to be in this tiny region here. Okay. Yeah, I'm sort of tired, so probably let me mention some open questions and finish here. So one open question is that we're not sure if our conditions are sufficient. So again, let me stress this again. What we are trying to look for is, suppose I have a region satisfying our condition 1, 2, 3. Is there a way to purify it, find another non-gravitational system such that this region is an island of something else? In our examples, it turns out that these are sufficient as well. At every point where there is a triple overlap, there is an island. It is an island of something else. We don't know if it's enough.
So when you say purify, yes. Are you saying canonical purification, or because purify is not unique, you can choose a lot of purification?
Exactly. That's actually
so what do you mean by
purify? So I gave you, say, for example, in this FRW case, I only know that I have a thermal state in the FRW patch. Where is it? And I have many ways to purify this thermal system, right?
Yes.
So the question is there a way to purify it such that this guy become an island? And indeed, like in this example, you see there are at least two, right? We found two cases where it is an island of something else.
But in your setup, you always choose this canonical purification, right? Like a Sommerfeld double case.
Yes. So I should say it's the false. If we don't succeed, we should look at other purification. But as we already find all of them to be an island, we just stop here. But you're right. You can consider it's highly possible other purification also give you this as an island.
But no, I don't think the logic is quite correct, because for given mixed state, which is a physical state, and all the properties should depend on the mixed state itself. The purification is just a trick, okay? In other words, it's not physical.
No, I don't. Like the point is this: the fine-grained entropy applies for region R, not for region I. That definitely depends on how you purify this system I.
Okay, maybe you are talking about different purification, but yeah. To me, I mean, if your given state, entire state is mixed state, if you want to employ this island formula, you have to do the purification. Otherwise, you cannot do it.
Yeah, but purification is not unique, right? As you said.
Right. That's why I'm asking that you have to choose some canonical purification.
You don't. I would say
in some sense is unique. Yeah. So then you can get some result which is entirely depend on your original mixed density matrix. I mean, entire one.
Are you saying whatever purification I choose, I should get the same answer?
If your initial state for whatever system, cosmology or black hole, whatever thing, the entire system, if it's mixed state, the answer is yes.
But we don't have a, like, for example, in this setup.
The answer, there's not quite yes, but I mean, you should choose a purification which gives you an unambiguous answer. That's.
Yeah, sure. But if you don't succeed with one purification, it doesn't mean it's impossible, right?
Yeah, but I don't think you should try. If you don't succeed, then you try another purification. If you don't succeed, you try another one. I don't think that's because you could have different answer, right? And that makes sense.
Yeah, that is different answer, I would say. it just means in this setup, it's impossible for this region. In one setup, it's not possible for a region to be an island. Doesn't mean it cannot be an island for any spacetime, right?
Okay, maybe we can discuss it in the end. We can discuss it.
Yeah. Okay, so let me first continue. So,
sorry, it was very brief for the last part about DS. So in that case, is that relates to the near extremal de Sitter-Schwarzschild black hole?
Yeah, it is. Yeah, it is.
It is near extremal. So then it is like Narian.
Yeah, exactly. It's exactly the Narian.
But then there's no singularity, right? Then there's no.
Sorry.
No. Then Nariae solution is you have, I mean, is unstable. Firstly, in neutral gravity, and secondly, well, it has no singularity, just DS2 cross S2. It has no singularity.
I see your point. Are you saying that you want to take the exact, like, even for the near extremal, like, limits?
Yeah. Yes.
I see.
Usually. Yeah. And also, yeah, the near extremal limit is Nariae, and Nariae is usually not stable.
I see. Yeah, that's actually possible. We are like, let's see how to say this. Well, you don't have to consider this high dimension point of view. This itself is a solution in 2D JT. Yeah, it's actually possible it's unstable. Yeah. That I actually don't know. Yeah.
Okay.
Yeah. Thanks for the comment. Okay. Yeah, shall I continue? Any questions? Okay. So one actually suspicion that these are sufficient is the fact that when we consider the second condition, like the first condition is actually in tension with the second condition. So you can violate the Bekenstein bound by making null wiggles of your boundary. But if you make null wiggles, the quantum extremal, like the second and third, the quantum normal condition is very hard to satisfy because the expansion at like the endpoint of the wiggle is essentially just infinity. So those conditions are very hard to satisfy. So we actually suspect that they are also sufficient, but we're not aware of a proof. Okay, so if it's sufficient, it's very interesting how to prove it, and also how to find other interesting islands. Do we learn anything more? If it's not, it's also interesting because we're sort of now convinced that quantum information constrains these islands quite a lot. But if there is other quantum information constraints, that would be great. And the next question, I think Janet might be interested because like the tensor network picture will tell you that even radiation dominated FRW, there is an island, but you just cannot extremize it. The extremality condition is never satisfied. So of course, this requires dynamics in tensor networks, but it will be very interesting if these conditions also have a tensor network picture. Yeah. The last thing is, well, 2D, it's just, this is just a toy model of inflation, but we wonder if we can do similar things in high dimensions. Of course, there you have to calculate entanglement entropy for high dimensions, and usually it's not known. So yeah, we leave it for the future. Okay, so okay, this is a summary slide. So I first reviewed the black hole information paradox and the quantum extremal island prescription. Then we use quantum information constraints, inequalities to give constraints on the existence of islands. There are 3 conditions, and these 3 conditions are very restrictive. They give very small overlaps and also sufficient in our examples in cosmology. And finally, we use them to find examples combining the constraints and also check directly there is an island. Okay, so that's it for my talk. Thanks.
Thank you very much. Are there any questions? There were lots of questions in the talk.
Can I ask a random question?
Yeah, sure.
So it's more like science fiction, but like, can we make some local measurements to tell whether we are on some islands or like whether we are on the radiation path that are secretly connected to some island?
This is a very good question, actually. We suspect that there are like twofold of the answer I can give you. First of all is we suspect that you can ask this question, suppose I have a spaceship, I have some qubit entangled, is it possible I just tune it carefully that I make it some island? And we suspect that by our conditions, you can probably prove before you make an island, you must form a black hole. This is the first answer. The second thing is, it's really the quantum nature of the entanglement that make it possible. Like, I think local measurement probably is not enough to tell like such non-local quantum like distinction.
Okay, thanks. Then, okay, thanks.
Sorry, following up on Yang's question just now, he was asking about purification. So is there some, yeah, that got me very confused because is there some assumption or what exactly is the purification involved between the radiation or the non-gravitational part and the gravitational part? It seems that this the actual choice of purification never shows up in the computation. So what do we know about that? Or
yeah, actually, yeah, I probably didn't make it clear. In the first part, like, okay, let me state it in the following way. Suppose I give you a space-time. I can choose to study matter in a mixed state in this space-time, right? Mm-hmm. Then I can just study these conditions. These conditions will tell you whether they can be island or not. But when you really try to extremize the entropy functional, the hybrid entropy functional, you need to know the entanglement entropy of the whole system, say, like on the whole Cauchy slice. And that is where the information of the purification comes into play. We actually do use it. This entropy function, for example, this F is only true for thermofield double.
So what is that purification? Or in other words, you F determines the form of the purification.
We do.
A thermal coupling between.
What about this? Suppose, let's see where it is. To calculate this S matter I union R, it's not always true that these formulas are what you will get, right? For thermostat, probably other purification of the thermostat give you similar answers, but for very complicated state, you don't expect all the purification give you the same answer, right?
I see. You're saying that suppose I compute this S matter I union R.
Yeah, that's the choice.
So, and that tells me something about the purification.
Exactly,
but
exactly.
The explicit form of R that I put in and then compute this object.
Exactly, exactly. On the other, so that's why it's a much, I think it's, let's see how to say this. It's a different question from our starting point. We sort of want to ask, well, these conditions don't refer to that choice at all, right?
Right, exactly.
Yeah.
I see. Are there other comments? I'm so thank you so much. I think it's fairly late for people in the East Coast. So if there are not other questions, then I will leave you alone. Thank you very much.
Okay, thank you very much. I will stop.
Yeah, thank you.